So now we will continue from where we left today. First of all, let us. So today we are going to complete little bit was left on the random vectors, and then we will go to random processes. Okay, that is a major concept because throughout the course we will be dealing with random processes. So let's first recall. Firstly, we had a confusion. Actually, that confusion was created today when I opened the book to see what was the confusion. I got the meaning in roughly 5 seconds. Just looked at the book and I knew where I was wrong. Where I was wrong is this. That is, if z is equal to gx, what we were saying yesterday, that if z is equal to gxy, and then once x and y are given, z is a deterministic function. So there is no expectation about it. I mean, if you take expectation, you will get that function. So that was our major confusion. So actually, this is not what was written in the book. Is actually I misinterpreted. What was written in the book is that I mean a sentence like this, that expectation zx given xy is a function of xy, therefore it is a function of xy. I mean, one same clause was repeated twice in a sentence. So the first one I interpreted it like this. That is not correct. So if you forget this, then this is very clear that expectation of z given xy is a function of xy. Okay, z is not a deterministic function of xy. Z is some random variable. X and y are some other random variables. All right. So then, if x and y are given, then you will get a different probability function. You get different statistics. So if you take the expectation of z given xy, remember that this expectation will be a function of x and y. And then if you take this expectation is what? This expectation is over x and y. Whenever you see these expectation operators, you have to mentally determine that this expectation is being taken over what? Over which random variables, which probability space. That is very important to think, because in general in the books they will not write that. They will just write E. Okay. In this case, so basically this is nothing but, you can say that, what is this? This is, you can write this as integral z f z given xy f z f xy xy dx dy dz. This will be, there will be 3 integrals, because finally what you are going to get is a number. Look at this. Finally what you are going to get is this one. See, the first expectation is z. What is the expectation of z given xy? It is z f of z given xy dz. Standard formula. What is the expectation? X fx dx. Now this, so the first one is, if you put this dz here, then you get the first one. Obviously it is going to be a function of xy. Now if you want to take expectation over both x and y together, then this thing will come. because this is the probability that x is between, capital X is between small x and x plus dx, and capital Y is between small y and y plus dy. So that you have to now take expectation, that is not expectation, you have to now, yes. So this thing now you have to vary over the probability, or for that is you have to do it for all possible values of x and y. So that's why another set of integral will come, these which will consist of these two terms. Okay. So that is what is being written here. So there is no confusion about it, only confusion was that this z is equal to gxy, that I wrote interpreting the book and I was in error. Okay. Once you do that, then for example here expectation of z given capital X equal to x. So one, you are now freezing. What is the difference between this? Here I am saying that if some value of x is given, what is the expectation of z? I am not saying what value, I am just saying that if some value of x is given. So then what will be the expectation of z? Obviously depends on what value of x is given. That is why it is a function of x. But here you are telling that the value of x is given, already told. So if the value of x is told, then what will be expectation of z given that value of x, right? So now this will be, this is a function of, what is this? This is the expectation of z given some value of x and some value of y. Further, if you give that the value of x is this, then you get this outer bracket thing. So it is expectation of z given xy is now a function of x and y, given that x is equal to x. Further, another piece of information is given, that is not only that function you are calculating, now you are putting the value of x in that function. So then this becomes a function of y. Now if you take this expectation, so then if you take this expectation, that means you have to now consider all possible values of y. So this expectation is now over y. Then you will finally get this, which should be a number again. So this is the interpretation. So always remember that you have to know that where over what you are taking the expectation. So I think this is clear now. So this point is cleared. So now we continue from where we left. Okay. So we were talking about vectors, and we said that as far as the probability is concerned, obviously vectors have a certain algebra. Vectors are certain kinds of objects. You can add them in a certain way, you can multiply them in a certain way, you can invert them in a certain way. So there are operators associated with it. There are rules of working with such objects, and they are collections of numbers, but they are not exactly like sets, which is like putting the numbers in a bag without any order, but which is like putting them in slots. You know, this is x1, this is in the first slot, that is x2, that is in the second slot. So the place is fixed, while in a set there is no place, it's just all in a bag. Okay. But as far as the statistics is concerned, they are pretty much like having n random variables together. So you have to always think of their joint statistics, right? So that's what we discovered, and then we were trying to see that, first we saw that if we are given one random vector x and if we are given another random vector x, both of which are defined on the same probability space and they are also related by a certain functions like phi and g, then how to compute that, then given the sort of fx's, that is given the probability distributions in the space of x1 x2 xn, how do we get the probability distribution of y1 y2 yn? That's what we saw, and we saw that you have to take the ratio of the volumes in the n-dimensional space here, and the ratio, these things we discussed in the last class, using what is known as the Jacobian and the determinant of the Jacobian, etc. So we did roughly up to this, I think this, then you have to, how do you calculate the expectation of a vector x? It is nothing but the expectation of the elements. So this is the mu1 mu n, where mu I is equal to expectation of xi. So you take element by element expectation, nothing else. So the expectation of xi is again defined by this formula, which is where you are keeping this xi and all others you are averaging on, and okay. Now then we define what is the covariance of x. This is an important quantity. Many times we will be evaluating this quantity for vectors, covariance. So the covariance is defined as, it is the variance is square deviation from the mean, as we know. Standard deviation is root mean square deviation from the mean. So this is deviation from the mean. This into this, for scalars you do square, and for vectors you do this into this transpose. So what happens actually, this is a written in vector notation, but actually what are these quantities? It will be a matrix. This is a column vector. Actually we should not write it, actually what I have written is wrong. This should be written as transposed, because there are two kinds of vectors. One kind of vectors are vertical, they are called column vectors. The other kinds of vectors are horizontal, they are called row vectors. In this case I am assuming that x is a column vector. I have merely written it as like this because the page is like this, otherwise it will take a lot of space to write. That is why I put transposed. So now what do you get if you multiply a vector like this into like this? You get a number, right? This is called a scalar product. This into this plus this into this plus this into this, you get a number, because this is 1 into n, this is n into 1, so by matrix rule it will be 1 into 1, so it will be a scalar. On the other hand, if you multiply this with this, you will get a matrix, because this is n into 1, this is 1 into n, so you will get n into n, right? So this is a matrix, and what are its elements? So what you are multiplying it is actually, can you see this? Okay, what I am writing you can see, right? So what you are multiplying is x1, let us say x1, x2, x3, you are multiplying with y1, y2, y3. So what you get is x1, y1, x1, x2, y1, no, x2, y1 is here. Yeah?
Elements of those vectors should be same.
Means? No, I am just giving a general example. Why elements of those vectors should be same?
I mean, sir, both are x minus mu.
Right, in this case it is defined like that. I am just saying that if you multiply a column vector by a row vector, in this case x1 is x minus mu, in this case y1 is also x minus mu. That is a special case. Okay, so x2 y1, x3 y1, then x2 y2, x2 y3, x1 y2, x1 y3, and so on. So in general the ijth element is xi into yj, right? So here also what am I getting? I am getting the expected value of the deviation of the ith component of the random vector x multiplied by the jth component of the random vector, same random vector x. So what am I trying to see in a way, and then I am taking expectation. So in a way what I am trying to see is that these various components of the random vectors, they in general, most signals, you know, this is very important, because in practice whenever you get a, suppose you are taking it from some circuit or something, so there will be a strong deterministic component, which is which arises from the circuit, the way you want to use it, etc., etc. And on that you are going to have some unpredictable things happening which you don't know why they happen. So your signal is generally going to look like this, right, when you are actually talking about signals. So if you have two such components, suppose you have another component like this, which is the other component of the vector, then what you are trying to see is that how are these increments from the mean. This will be in general the mean. That is, if you see, mean has again two interpretations. Often when we talk about a deterministic signal and say its mean, we often mean that we are talking about its time average. That is, we take averages of time and then average it over time. That is a kind of mean. In this case, what are we talking about? When we say mean, we are talking about experiments. So we are talking about ensemble average. That is, these are two different things. So when we talk about means here and expectations here, expectations are also averages, but they are ensemble averages. That is, if you create 200 instances of the same thing by doing repeated experiments, then what you get is an ensemble. Some people pronounce it as ensemble. Okay, so you take an average over those. Okay, so what it means is that you first conduct the experiment one day, suppose you get these two curves, then you conduct the experiment on another day and you get maybe the same curve, but now these things are going to be different on another day. So you do these experiments and then suppose you take at any point of time, suppose you take the increments. This pen does not write. Okay, so what you are saying is that these variations about the mean in the component x1 and the variations about the mean in the component x2, are they correlated? That is, if one is positive, does the other, on an average, is it positive also? That's what you are trying to see when you are seeing covariance. And this is very important, right? You are not talking about their means, because means you have already subtracted. So you are only talking about that random part which is beyond the mean, and you are trying to see whether that random part is correlated or not, right? So that is the physical meaning of this, and we are in many cases interested in that quantity. Similarly, you can define what is known as correlation. R is, here we have not subtracted the mean. So when we take correlation, we directly take XX transpose. We are trying to see the whole signal. And you can easily just by simple algebra you can prove that covariance of X covariance is related to autocorrelation like this. This is very simple algebra. Just X minus mu into X minus mu transpose you open out by explicit multiplication. You will get this. And now there are three different concepts which are sometimes used. For example, what is meant by two signals are uncorrelated? Two signals are uncorrelated means that expectation of xy transpose is equal to expectation of x into expectation of y transpose. That is, this is equal to this. So that means that this is equal to 0. If what is this correlation? Actually, this is sometimes called autocorrelation. In general, you can calculate this for two different signals. When in both places you write x, you are finding the correlation of one signal with itself. That's why you have written x in both places. That is why it's called autocorrelation. In general, you can write x here and y here, or y here and x here, in which case it will be called cross correlation. Okay, so in general, if you talk about, so if this cross correlation is equal to mu x into mu y, this is mu x into mu y transposed, that means this equal to this, that means this equal to 0, in that case it will be called covariance of xy. So then that equal to 0, what does it mean? That the covariance of xy equal to 0 means that the increments of the it is 0. It is 0 means what? It is 0 means it is the 0 matrix. Covariance is a matrix. What is meant by a matrix is 0. It means that every element of it is 0. So it means that if you take an arbitrary component in x and take its variation from its mean, and take another arbitrary component in y and take its variation from the mean, if you take their correlation and then take expectation, it will be 0 for all components, any pair of ij's, right? If it is orthogonal, then expectation of xy transpose itself is 0, right? So then this itself is 0, which generally means that it does not have it will probably not have a mean, because if things have a mean, then their correlations will tend to be, well, at least one of them will have to be 0 mean. Otherwise, getting a correlation of, if they have a persisting mean, then getting their correlation as 0 is difficult. So expectation of xy transpose is, then it is called orthogonal. Actually, two vectors are called orthogonal if then their projection becomes 0. And there is something called independent. Independent means that probability distribution wise they are independent. That is, the joint probability density of x and y can be obtained as simply as the product of the two joint probability. That is which means that in the underlying experiment space, these two experiments have no relation, have no bearing with each other. Maybe you are tossing a coin here and then you are casting a die here, and then you are combining this result to make your experiment. Tossing a coin has no relationship with tossing the die. So which face of the coin comes up? So I mean saying that what is the probability of having a head and a 4 coming up on the die is simply nothing but the probability of having a head multiplied by the probability of having a 4. They are disjoint events, so their probabilities are multiplied. So right? So in such a case you call them as independent. These terms will sometimes be used, so that is why this is the meaning. Now if you have independent, see, this is the most strong condition. If this happens, then so independent will mean that they are uncorrelated, obviously, because they are coming from totally different experiments which have no relationship, and the experiments are random and you are subtracting the mean. So then what is happening around the mean is they are not related. So if you take many cases and you average, it will come to 0, right? But uncorrelated will not mean that they are independent. That may not happen. So these are, we will see them in much more detail, but these are some terms which are used. Now we come to one of our very important concepts, that is the concept of a random process. See, first we said that the underlying space is always the same, that you are performing some experiments and you are getting outcomes. Those outcomes are xi's. Okay. Now in the case of random variables, what you did is for every outcome you picked a number x. So for every xi you picked a number x on the real variable, and you said that therefore this real variable is a random variable. So remember that for every outcome you are picking a number in the case of random variables. In the case of random processes, for every outcome I'll pick a function of time, right? So I'll pick a different function of time every time. So what is happening is, so suppose this is my t axis, okay, function of time, we are, because in engineering we are mostly concerned with functions of time. In statistics or in economics they are more concerned with, they are also sometimes concerned with functions of time, but they are very often not concerned with functions of time, but simply with random variables. But in engineering, especially in signal processing, what is a signal? It is a function of time. So our prime object of interest are random functions of time. So that is why these random processes are, that is the central concept, and we all the time we have been climbing to come up to this concept. So here we have the t axis, and here we have the what is known as the xi axis, and this is my, so I am now defining a function of time. For every xi I am defining a function of time. So whenever I am getting a xi, I am mapping and getting a function of time. So what are those functions of time? Those functions of times are whatever, some function of time. So for xi is one xi, this is the xi axis, I am getting this function of time. For another xi, I will get another function of time. For another xi, I will get another function of time. These together is the random process. You know, there are circuits which you get which will generate random functions of time. They are called noise sources. They are used to calibrate instruments in communication engineering. We have them in our labs. So if you take a noise source and today come and switch it on and then see the function on the CRO, you will get one function. If you come tomorrow and then again switch it on, you will get a different function of time. It's like that. So the output of that noise source is a random process. Okay. So basically this is the first concept, that it is a function of time. It is a mapping. Every time I am given out an outcome of an experiment, I have to pick a function of time. Previously I was picking values. So now that means now my random process x becomes a two variable thing. For every outcome I am getting a function of time. So it is now a function of x of t and xi. Agreed? So this is an ensemble of functions. It is an ensemble of time functions. If you freeze this, that is, if you see for a particular outcome, what you get is a simple function of time. It becomes some xt if you freeze xi. If you freeze t, what does it become? That is, if you switch on that noise source and every time just see the value at 2 seconds. Every day you come, switch it on, you get a new function of time, just see the value at 2 seconds every day. So you are freezing the time, but you are doing an experiment over and over. So you get a value here, you get a value here, you get a value here. So if you take all these values, what is it? It is a random variable. When you freeze time, it becomes a random variable. It is a random variable for time t is equal to 2 seconds. You will get another random variable at time 2 equal to 3 seconds, another at 1 second. So if you freeze t, it becomes a random variable, and if you freeze both, it becomes a number. If you freeze t and xi both, then it becomes a number, 1.5 volts. So if you freeze both, it becomes a number. If you freeze xi, it becomes a function of time. If you freeze t, it becomes a random variable. If you have both floating, then you have an ensemble of time functions in general. So it's a process which is capable of various time functions, okay, which are uncertain. That is a random process. Agreed? Now every time, now we will be talking of our, our standard quantities of interest that talk about, that is, we will be defining fxt. So what does fxt means? It means the probability that xt becomes less than or equal to x. That's why now it is a function of t. So what is the, so as if you are saying that if you switch on, then suppose you are saying that what is the probability that I will get a function whose value at 2 seconds is going to be less than 1.2 volts, if you are saying like this. So at t you are saying that the value of the function will be less than or equal to a particular given number, say 1.2 volts. And if you perform repeated experiments, what is the probability that this is going to happen at 2 seconds, at 3 seconds, at 4 seconds? If you characterize that, then that is the distribution function of the random process, right? And naturally its density function is going to be del f by del x. That will be, that is, this into dx is going to be the probability that at t the value is going to stay within 1.2 to 1.21 volts. What is the probability? Previously I was saying that it will be less than 1.2 volts. Now I am saying that what is the probability that the function at t equal to 2 seconds, the function value is going to be within 1.2 to 1.21. That is going to be this into dx. Same interpretation, absolutely same interpretation. Only since we are dealing with functions, we have to always talk about t here. But it is, always you can nicely go back to the probability space. The moment you freeze t, you get random variables. So you are back to your more comfortable region, right? So
in this function we have both x and t variables.
That's right.
Why not dou x by dou t also?
Yeah, you can do that. But then yes, you can do that. That is if you want to differentiate this, then if you differentiate this with respect to time, what is the physical statement you are making? That how does this probability vary with time? That is, how is this probability going to change if you measure it at 2 seconds and if you measure it at 2.01 seconds? If you are interested in that quantity, you have to take dou x by dou t. Yes, true, correct. So we can, in general, we will get more than one values. We will get more than one random functions. You can have, in this case, have. So if you have x1 and x2 as two different random processes, then what is their joint distribution function? That is going to be probability that x1 at t1 is less than or equal to small x1 and x2 at t2 is less than or equal to small x2. That is the interpretation, physical interpretation. And now it is going to be a function of x1, x2 and t1, t2. It will be a function of four things, correct? We'll have to see examples of this, but we'll see them in the tutorial. There are if you get any of the textbooks, there are large number of examples. So you can go through them. We'll see them in the tutorial. But now we have to quickly converge this, so I am not going into examples. Now in general we are more interested in expectation, expected values. We are always, estimation is about finding likely things. So what is expectation of xt? It is this. It is again a function of time. Now everything has changed to now functions of time. Previously we were having a random variable, so its expectation was becoming a number. Now we are having an ensemble, we are having a random process, so its expectation is a function of time. So it's now mu t, naturally, because the expectation is over x. So x will get eliminated and you will get t. Obviously, so at each point you are going to have a different mu, naturally. In many cases now, so you can define now, just previously we were defining correlation of vectors. Now we have vector functions of time, that is x1 and x2. So you can now define correlation. Now if you want to, you see that if you have our previous drawing, that suppose you have one random process which is this x. Okay. Now you have another random process which also is generating these things. So now if you say, if you freeze time t, then you get a random variable x1. If you freeze time here, you will get another random variable y1. If you put them as components of a vector, you will get a random vector, right? So you can get vector functions of time also, no problem. We have, which are basically, if in a vector, if you put each component as a scalar random process, then you get a vector random process. Basically you are taking the signals and putting them in slots again, just like you are putting variables in slots. Now you are putting functions of time in slots, so you will get a vector function of time, correct? So now here similarly, if you are given two different random variables, you can now say what is their correlation. But now when you are saying what is their correlation, you have to say that you are taking this correlation between which 2 points of time. You can take a correlation between xt1 and xt2 in general, right? So if you take now expectation, then it will be a function of t1 and t2. That is, you can say, suppose there is something that if this is positive now, then after 2 seconds it is going to be positive. So if you take t1 equal to something and t2 equal to t1 plus t2, maybe they will be strongly correlated. In between maybe it varies. Such things can happen. So when you take correlation now, because now it's a function of time. So when you are taking expectation, you have to say between which times you are taking. What is t1 and what is t2, because this correlation will change depending on your t1 t2 choice, right? So therefore now when you define correlation, you have to say Rx(x) of t1 t2. This times you have to mention, which will be this thing. So I am multiplying them and I am taking their joint densities at t1 and t2 and taking expectation, same thing. Similarly, we can take, this is the correlation. You can take covariance, where you are subtracting the mean. Same thing. We know that for covariance calculation we always subtract the mean, and for correlation we don't subtract the mean. So these are exactly same thing. And just like the previous thing, you can also say that Rx(x) t1 t2 minus mu t1 mu t2 is going to be covariance x t1 t2. This is again algebra. You just multiply it out, you will get, and you take expectation, you will get it. So these are, all I am trying to say is that you have absolutely parallel definitions. Only you have to keep track of the fact that now what you are dealing with are functions of time. So t1 and t2 will come into play. Again, you can have definitions of orthogonal, which says that this is equal to 0, of uncorrelated, which says that the covariance is to be 0. They may both have 2-volt means, but their excursions about the mean is going to be that I'm going to be uncorrelated. And similarly, if you have independent, now this brings in the major complicacy of random processes. See, in any random process, even if you have the whole problem is that even if you have only one random process, what you have is an infinity of random variables immediately, because it's a function of time, and time extends from minus infinity to plus infinity, and for each of those times you are getting a random variable. So immediately, even if there is only one random process in the picture, the number of random variables shoot to infinity straight. So it's a much more, it's like increasing the dimension of the space. I mean, the moment you have a plane, you have an infinity of lines, so because you have increased the dimension of your space. So here also you are adding one dimension, which is the time dimension, which is infinite. So obviously you will get an infinity of random variables. So now if you say independent, this is a very strict condition to be satisfied. It says that you choose any arbitrary number of time points t1, t2, t3, any number, either 2, 3, 4, 20, and you take samples xt1, xt2, xtn, they are going to be random variables. The moment you freeze time, it becomes random variable. So you choose an arbitrary number of time points. So you get an equal number of random variables in x. You choose another arbitrary set of time points, and you choose from y. So now you have t1 to tn and t dash 1 to t dash 10 number of random variables. And so naturally now you have to study their properties. Means you have to study that how these random variables behave over experiments. You have to study. You have frozen the time points now, so you have got some variables. Now when you will try to understand their statistical properties, then you will see how these set of random variables are going to behave over experiments. So then that is characterized by their joint probability densities. So if you calculate the joint probability density of this, they are mutually independent, means that fxy is equal to fx into fy. So their joint probability densities are going to be guided by their individual probability densities only. That means that they come from unconnected experiments, and this is going to happen for arbitrary number n and for arbitrary choice of time points t1 to tn. You take any number choose any number n, and after you have chosen n, you choose as many number of time points arbitrarily. This must happen. Only then these two processes will be called statistically independent. This is a rather difficult condition to satisfy and check, but mathematically that means that means here their variations at all points of times are they are not only random in time, they are also random amongst themselves. So that is the definition. Now we don't know, I mean, these things are mathematical concepts, but they are in general difficult to satisfy. Very difficult to satisfy. Only why they are considered is that once you can choose them, the whole problem is that if you want to characterize the behavior of these random processes in statistical terms, then you have to always talk of their joint probability densities. And their joint probability densities, each one will be different. Suppose you take t1 equal to 1 and t2 and t dash 1 is equal to 3. Then there are two random variables, they will have some joint density. The moment you change t1 to 1.1 and t2 to 1.9, they are now two different random variables. So in general they can have a different density. So you will get an infinity into infinity number of density functions. So that's a hopeless case actually. I mean, you can't even deal with it properly. So that's why mathematicians make various kinds of assumptions to see how to simplify matters, at least get some results. Making things very generalized usually does not help. That's why we are throughout your controls course you are so obsessed with linear systems. Why? Because by making the assumption of linearity, you can at least get some results. If you don't make the assumption of linearity, in many cases you can't get any results. It's very difficult to prove stability. It's very nonlinear system stability in general you have to find a Lyapunov function. Now how to find the Lyapunov function, nobody knows. If you can find it, you can prove it to be stable. So complexity will increase. That's why people have tried to simplify matters, and assuming that two processes are independent simplifies a lot of maths. Simply because now you have their joint density, that is, you can reduce one dimension. Joint densities will be simply this into this. So if you know each one's individual density, the combinations are not going to be different. You can generate the combinations from the individuals. That is an advantage. So for such reasons people make these assumptions. Okay. So now we are talking of another thing. Again, that this concept has come because we want to reduce complexity. We have two dimensions. On one dimension, which is the value dimension, that is the signal's value, that itself is uncertain, and another dimension is time. So now what I am saying is that can I do something? Can I make some simplifications on the time dimension as well? then I can deal with things. So that's why people talk about this concept of stationarity. So people say that on the time axis things are going to be regular. There is some regularity that you can expect on the time axis at least. That simplifies matters for you. So they are saying that a function is strict sense stationary in the real strict sense if the density function fxt does not vary with time. So you evaluate it at t, evaluate it at any t plus c for all c. Immediately you have made a big simplification. You are saying that the property of these random variables at any point of time are the same. They are different instantiations, as if underlying you are having only one experiment. So when you are generating the value, you are casting a die and then generating a value 1.1. When you are generating the next value at a different time, you are again casting the same die. So all the numbers are actually coming from the same experiment. So they have the same probability distribution. It does not depend on time. Immediately you see the amount of experiments are totally reduced. Previously at each time you are doing a different experiment, having a different density. So one infinity you have reduced. Previously you are having an infinity of experiments. Now you are having one experiment. That's a big advantage. So, and not only that, they are saying that they're also saying that the joint density function for T1 and T2 will in general not you see, everything is invariant to shifts in time by a constant shift in time, but that constant can be different. I mean, that constant can be anything. That is, if you take this at T1 T2 and then take the same function at T1 plus C and T2 plus C, they are going to be same. That's what they are saying. So what does that mean? It means that I mean, C can be anything. So it essentially depends on what is T1 and what is the difference between T1 and T2, because when you are shifting, you must shift T1 and T2 both by the same amount. So which means that when you are shifting them, what are you keeping constant? You are keeping the difference between T1 and T2 constant. You are shifting T1 and T2 both on the axis. So the function essentially depends on T1 minus T2. It does not depend on the absolute value of T1 and T2. That's what it says, right? So we will talk about autocorrelation functions, which previously we were saying Rx(x) T1 T2. We will say that it does not depend on T1 T2. We'll talk about Rx(x) tau, where tau is equal to T1 minus T2. That again simplifies one dimension. So, and then you can have a, this is also very difficult to check. Who is going to check all these joint density functions? Very difficult to check. So we'll have to continue this. So let's stop here. All right. Thank you very much.